Hello everyone, welcome back to the MOOCs course on Advanced Analytical Technique. We are now entering into the third week of this course, and this is the first lecture of the third week, where we are going to discuss about the inductively coupled plasma technique, which is used as a source of excitation in atomic emission spectroscopy. My name is Dr. Mohammad Zain Khan, and I have been working as assistant professor in the Department of Industrial Chemistry, AMU Aligarh. With the let us begin with today's lecture. Inductively coupled plasma technique, or the ICP technique, which is coupled with an AES and used as an which is coupled with an atomic emission spectroscopy technique and used as excitation source. This ICP is also known as ICP AES. The integ the integ sorry the in, the inductively coupled plasma technique, which is also known as ICP-AES or ICP-OES, which means that inductively coupled plasma atomic emission spectroscopy or inductively coupled plasma optical emission spectroscopy. It is one of the widely used method of AES technique. Among all the possible excitation sources like the flame excitation sources, our electrothermal methods like electric arc, AC arc, AC spark and DC spark, AC arc, DC arc and AC spark, we always prefer to use plasma sources because with these sources we can attain very high temperatures, and these techniques are also um, amenable to multiple element analysis simultaneously. And among the available plasma techniques, two we have covered in the previous lecture: the direct current plasma, the microwave plasma, and then the ICP, inductively coupled plasma. This ICP is one of the widely used technique because we can achieve very high temperature, even up to 10,000 degree Kelvin by this technique, and it is very useful for multiple sample analysis. It has been used for over 30 years and it is considered as one of the most versatile method for the inorganic analysis, means for the analysis of elements. And with this technique we can analyze all alkali metal, alkaline earth metals, transition metals, metalloids, lanthanides and few actinides by this technique. Even carbon, nitrogen, oxygen and sulfur, these non-metals, can also be analyzed by this technique. For it is one of the most versatile method for inorganic analysis, which means it can be used for the analysis of elements like alkali metals, alkaline earth metals, like alkali metals, alkaline earth metals, transition metals, metalloids can also be analyzed by this technique, and we can also go for lanthanides as well as few actinides. Further, some non-metals like carbon, nitrogen, oxygen and sulfur are also uh, studied by ICP technique. Just like direct current source plasma and microwave plasma, it also uses an argon gas, an inert gas like argon, to create this plasma, and it provides very high accuracy, as well as it minimizes the possibility of formation of oxides as well as nitrides of the metal at such high temperature of over 10,000 degree Kelvin, because we are not using oxygen or any other oxidant, we are using an inert gas. So the possibility of formation of any compound like oxides of the metal, so the possibility of formation of any compound of the metals like metal oxides or metal nitrides is very low. This ICP uses a plasma torch. This is the plasma torch, which is basically used to create the plasma, and this plasma torch is made up of quartz. For those who are not aware, quartz is a silicate. It is a polymer of SiO2 in which the tetrahedral units of Si4 4 negative, are connected in such a way that each and every oxygen of this silicon tetrahedra is shared with other nearby tetrahedra to create a network of structure, and it is represented by SiO2 silica. It is a polymer of silica SiO2, and this is having very high thermal stability. So this quartz, and it is very high optical property, it is transparent like glass, so it is transparent, it has very high optical property. So this quartz tube is used, and this quartz tube, it is it contains 3 tubes concentrics, and it contains 3 concentric quartz tube, means we have an outer tube, then we have a middle tube, and finally we have an inner tube. So there are 3 tubes. As you can see, this is our inner tube, then this is our minor tube, and this is the outer tube. In all these 3 tubes we passes argon gas, which has different purposes. In the outer tube we passes argon gas, which serves as a coolant gas to maintain the temperature and to avoid the damage of this quartz torch or these copper coils, which are used as a coil for passing radio frequency. In case of ICP, just like we use microwaves in case of microwave plasma, in case of ICP we uses radio frequency source to create very high magnetic field that has the potential to convert an argon gas, an inert gas, into its ionized form to create a plasma. So in ICP we use radio frequency, which creates very high magnetic field, and that ultimately creates a plasma. So this torch has this torch has these radio frequency coils that are made of copper, which are used to pass the radio frequency from the radio frequency source. These coils are connected with a radio frequency source, and they are used to pass radio frequency. Then we have, as I said, 3 concentric tubes of quartz. The outermost tube is used for passing coolant argon gas to maintain the temperature. Then the middle, the second quartz tube, the second concentric quartz tube is used for passing auxiliary argon gas. The purpose of passing this auxiliary argon gas is to create a plasma. So we need high flow rates here, because high flow rates can only be able to sustain such a high plasma. And then this inner tube is used for passing aerosol sample, which are already prepared in argon gas. So as I said, the torch, which is made of quartz, consists of 3 concentric tubes, and the outermost tube has a diameter of 2.5 centimeter. This has a diameter of 2.5 centimeter. So this tube, it is the outermost tube, which has a diameter of 2.5 centimeter, and it is used for passing coolant gas to control the heat. Argon gas in the outermost channel is used for controlling the heat, while the argon gas in the middle column is used to create the plasma. And these argon gas moves tangentially. These gases moves in a tangential manner, so as to completely cover up the quartz tube and provide cooling to the whole tube structure. This gas which is passed in the middle column is called as auxiliary. This gas which is passed in the middle column is called as auxiliary gas, and it is used for creating the plasma. Now, as I said, the torch is already connected with copper coils, which are connected to the radio frequency source. So we have radio frequency source, also known as radio frequency generators. Radio frequency sources are sources of electromagnetic radiation with very high wavelengths. They are also used in communication services, so they have very high wavelength. These radio frequency sources are used with frequency ranging from as low as 5 megahertz, because even at 5 megahertz it has sufficient energy to create a high magnetic field, which is able to create a plasma. And we can go up to 100 megahertz of frequency, which is of course a very high frequency value for our radio frequency region, and at such a high frequency of 100 megahertz or 100 into 10 raised to the power 6 hertz, we can easily create a high temperature with the help of a magnetic field that is capable of converting an inert gas like argon into its plasma. Although the frequency ranges from 5 to 100, but for practical purposes we generally use a RF generator with frequency of 25 to 40 megahertz. It is very common, and these frequency and external power source are basically responsible for creating a magnetic field which then generates a plasma. And these frequency and RFs and these RF frequency and these RF frequencies are transferred to the quartz torch with the help of copper coils, and these copper coils are surrounding the quartz tube, and they are being protected from the high temperature of the plasma by a circulating water bath around it. So along with these coils that are surrounding the torch made of quartz, we also passes circulating water which protects this coil from burning. So this is the assembly. Here you can see we have a plasma torch. This is a spray chamber which is connected this is spray chamber sorry this is spray chamber which is connected to the nebulizer sucks in the sample, mix it with argon gas. This is argon gas supply, so nebulizer sucks in the sample, mix it with argon gas, and then spray the aerosol in this chamber, and with this chamber the aerosol enters into the plasma, and finally this sample aerosol molecules are desolvated, vaporized, converted into their individual atoms, and finally excited to create an emission spectrum. Now as I said in case of direct current plasma, as well as for microwave plasma, where we require an argon source of 5 to 10 liters. In case of direct current plasma, we need a 5 liter per minute flow rate of argon, while in case of the microwave plasma we can go up to 10 liters per minute of argon. This much flow rate is required, while in case of ICP, inductively coupled plasma, we need excessive high rate of plasma, because here but in case of ICP we need excessive high rates of argon gas, because here the argon gas serves three purposes. The first purpose or the function of argon gas is to convert the sample into the first purpose of this argon gas is to convert the sample into aerosol. Then and it enters into the inner column of the quartz tube. We also pass argon gas in the outer chamber or in the outer tube, where it serves as cooling gas. Outer tube. The flow rate in the outer tube is around 13 to 20 liters per minute. Then it is also used, and then it is mainly used to create the plasma, where it is passed through the middle tube and called as auxiliary gas in the middle tube, where the flow rate is ranging from 5 to 20. Mostly we use 10 to 20 liters per minute of this gas. So the flow rate is 10 to 20 liter per minute here, then 13 to 20 liter here, and then also for creating an aerosol. So very high flow rates are required, even higher than our other plasma making techniques like direct current plasma and microwave plasma. Therefore such a high rate is maintained with the help of a Dewar apparatus. As I told you earlier about the Dewar apparatus, that it is used to store gases under cryogenic condition, means those gases which have very low liquid temperature. In case of argon, it is minus 185 degrees Celsius, In case of nitrogen, it is 196 degrees Celsius, and in case of helium, it is even lower, minus 260 degrees Celsius. So these gases can be stored with the help of these Dewar separators. These gases can be stored in liquid form with the help of this Dewar's flask, which is a flask made of either which is a flask made of iron, which is a flask made of stainless steel. And this stainless steel flask has a double walled structure, means it has two walls. This flask is made of two walls of stainless steel, and in between these two walls vacuum is created, because vacuum helps us to control the heat losses or the flow of heat due to convection and conduction. So this portion, this is basically the vacuum filled region. This portion is basically, these are the two. This is the inner stainless steel flask, this is the outer flask, and then in between we have this portion. Then this portion is for us to create the vacuum, and in this vacuum, this helps us to stop the flow of heat due to conduction and convection. And then in the outer part of this stainless steel, we provide coating of silver, which reflects all the heat, so that the flask does not absorb any heat, and it does not have any temperature effects, and it keeps the and it does not have any temperature effects and it does not have any temperature effects and it keeps the sample at very low temperature. So this Dewar's flask is used to store liquid argon gas that can be very helpful to meet out such a high demand of argon gas. If we calculate the total flow rate, if we calculate the total argon gas demand, it is around 40 to 50 liters per minute, which can be maintained with the help of this assembly or Dewar flask. Now the formation of plasma, as I just mentioned, that our quartz torch is having these copper coils supported with circulating water to protect them from damage, and in this we have three concentric tubes. So when the auxiliary argon gas passes in a tangential fashion into the middle column, into the middle tube, it moves up, and through these coils radio frequency is transferred into the torch, and the oscillating field of this radio frequency, or I should say the oscillating magnetic field of this radio frequency, and this oscillating magnetic field of the radio frequency provides excessive energy, which is sufficient to convert argon gas into its cations and electrons. So when through these copper Tesla coils, and through these Tesla coils, when we pass radio frequency, which has a fluctuating magnetic field of very high strength, this has enough energy to convert the argon gas coming as auxiliary gas in the middle tube, to convert it or to ionize it into its cations and electrons, creating a plasma which has very, very high energy. We can go up to 10,000 Kelvin easily, and immediately it can excite all the sample, convert all the molecules into individual atoms in excited state, thereby emitting light radiations, creating an emission spectrum. But as I said, proper supply of argon gas should be maintained, as well as for the sustenance of this plasma, the magnetic field available through this RF source must be stable. Then only we can generate a stable plasma which is sufficient to convert all the sample, even in multiple analysis, that is sufficient to create the refractory metals with very high melting point, into their excited atoms, creating or forming an emission spectrum. The appearance of the plasma. The plasma appears in the form of this, in this conical form, and the distance it the plasma itself generates a continuum of background radiation. So the plasma is very bright. It as it emits a continuum of bright light, but as the distance of this plasma from the coils increases, for example, we have coils placed over here, Tesla coils, and the plasma is generated here. As we move from these coils, the brightness of the plasma decreases. Although the temperature is still very high, but the brightness decreases. Brightness decreases as we move from the coil above at a distance of around 3 centimeter. The plasma is almost transparent. So in that transparent region, a point somewhere here, we carry out the analysis. So our sample is directly entered at this point, so that it immediately comes in contact with the plasma when the region is transparent, so that the chances of background radiation or the chances of absorption are minimal, or there are no chances of absorption or background radiation. So the sample with the inner tube in the form of aerosol enters at this point, which is at a distance of around 3 centimeter from the coils, so that at this particular point the plasma is almost transparent. Here you can see, first of all, when the sample enters into the plasma, this is the sample that is being injected in the form of aerosol. First of all, we have drying, which means removal of solvent. The solvent is removed, then it undergoes vaporization. The sample molecules which are in the form of aerosol, now since the solvent is removed, they are converted into their vaporized form or the vapor form. Then they are atomized, means the molecules are converted into their individual atoms, and then finally these atoms are ionized, creating electrons and cations. So this is our cations along with electrons. This is basically plasma. So in this plasma we have argon gas, some electrons, even some unionized argon gas, and if there are any other species, although we avoid having some other species, but if in case we have some molecular species that are still left, then we have traces of those molecular species, but we mainly have argon gas cations, electrons, and some of the unionized argon gas. And as I said, the region above 3 centimeter of this coil is transparent, and in that transparent region only we carry out the analysis. Now let us come to the instrumentation of ICP, inductively coupled plasma technique. Again, ICP, since it is a part of AES, atomic emission spectroscopy, so our ICP, inductively coupled plasma, or sometimes called as ICP AES, inductively coupled plasma atomic emission spectroscopy, consists of components that are similar to the components which are used in AES. For example, we use nebulizer here, we use although light source is not needed in AES, so here also we do not need a light source, we need excitation source, and ICP itself is an excitation source. So along with ICP we need a nebulizer, then we also need detector and monochromators. Sometimes since ICP is useful for multiple analysis at a time simultaneously, since ICP is useful for multiple analysis, multiple element analysis simultaneously, so instead of monochromator we can also use polychromator, and with polychromator we do not use photomultiplier tubes as a detector, because one photomultiplier tube can analyze one element at a time. So in that particular case, for simultaneous analysis of numerous, or for simultaneous analysis of multiple elements, we always use charge coupled devices, which are present in solid state array detectors, SSA detectors. Anyway, so this ICP is also used for quantitative as well as qualitative technique. Means we can know, means we can identify the type of sample, its structure as well as behavior, and we can also identify its quantity, the concentration or the amount of the sample. Again, just like all AES technique, it first of all converts sample into aerosol by mixing it with inert gas argon, and then the same argon gas is used to convert the, to create the plasma, which burns, which excite this sample to create an emission spectrum. The excitation source causes atomization as well as excitation. Atomization means the sample molecules are converted into individual atoms, and then they are transferred into excited state, and then sample elements creates an emission spectrum when their electrons returns back to the ground state. As I just mentioned, the components, as I just mentioned, the instrumentation of ICP AES is same, just like any other AES technique. We have an excitation source, which is ICP in this particular case. Then we have nebulizer, monochromator, detector, and finally an output device or a readout device, which is our computer. And we also have an output device, which is our computer. This is the flow sheet of the different components. We have a sample container over here, which is connected to a nebulizer. The nebulizer inlet pipe is immersed into this sample. The nebulizer sucks in the sample. Then we have a provision for argon gas in this nebulizer. Nebulizer mixes the sample with argon gas to create aerosol of the sample in argon gas. Then we have RF. Then we have ICP torch, which has outer jacket for coolant argon gas. Then in the middle tube we use auxiliary argon gas to create the plasma, and in the central tube our aerosol sample, where the sample is mixed with argon gas, is entered. It is excited, it is atomized and excited in the plasma. Then it reaches to the monochromator, where selective wavelengths are being allowed to pass through it, while some of them are excluded. Or even if we are doing multiple element analysis, we can use polychromators over here. So polychromators can also be used. And then finally we have a detector. For single element we can use PMT, photomultiplier tube. For multiple analysis we can use charge coupled devices, which are a part of solid state array detectors. So we use for multiple analysis we use solid state array detector, which have charge coupled devices. And finally we have an amplifier, and then the output device to present the spectrum, and then the output device to present the spectrum. So this is all about the instrumentation of ICP in brief. In the next lecture we'll discuss all these components, and especially the polychromators and CCD devices in details, because in the previous few lectures we have studied about nebulizers, we have also studied about the photomultiplier tube detectors as well as monochromators, but so far we have not yet studied about the polychromators as well as these charge coupled devices, which are a part of solid state detector. So that we'll discuss in our next lecture. Till then, thank you very much.